Hello student to the Foundation of Classical Electrodynamics course. So, under module 3 magnetostatic we have lecture 50 today where we are going to understand the Biot-Savart law. Okay. So, we have today class number 50. So, before going to the Biot-Savart law, so let me quickly remind what we have done so far. So, if we have a closed volume and try to capture the magnetic field lines, we will see in the last class that magnetic field line is like this. So, it do not begin or there is no like source or sink kind of term we can expect. So, I can write that the divergence of B is equal to 0. That was the thing we find in the last class, and that means magnetic monopole does not exist. That is why we are getting this result. Well, before going to the Biot-Savart law, we need to discuss once again this continuity equation. We did it in a initial class. So, in continuity equation, before going to the continuity equation, let me write down the equation first. Again we will like to prove it, that divergence of J plus del rho del T is 0. That was the relation we have with the current density and the volume charge density. So, we will do it once again. We prove it earlier, but we will do it once again. So, J, the current density, is written as rho multiplied by the velocity. This is the way we write the volume current density. This is called the volume current density. And in terms of volume current density, if I want to write down the total current, so it should be like this, J dot ds. So, I have a cross section, and in this cross section the volume current density is flowing, and if I integrate over this cross section with entire surface, then I will get the total current. So, the figure can be understood like, suppose I have a wire, like a cross section of the wire like this. And I have a small strip here. Suppose let us make this strip like different color. Like this. So, this area I write A perpendicular because I am making a perpendicular cross section, and the current density is J, and this is the direction of the flow of the current, say this is the flow, right. So, J here is simply di dA perpendicular. Okay. So, the charge per unit volume now charge per unit time, let us leaving a volume V is this quantity. Which is simply integration of the divergence of J dV. So, this quantity J dot I is the basically the current, but I am saying that charge per unit time, that means the current which is leaving in a volume V, and that means there is a flow of the current, and that we can write in this way, and this is simply the corresponding volume integral, because this is a surface integral. I am using just the Gauss's law to execute that. Now, total charge, now the charge is conserved, right. So, that means whatever flows out at expense of what remain inside. So, something is flowing out, but charge is conserved. So, that means whatever is flowing out, that should be as expense of whatever is there already in the inside. So, there will be a decrement of the charge inside. So, if I try to write in a mathematical language, then the volume integral of the divergence of J over dV, that should be the reduction of the charge density per unit time, the reduction of the charge per unit time rather. So, that means it is d dt of total charge, I can write as rho dV here. Okay. So, that is the expense of this amount of charge, we are getting the flow in terms of this divergence form. So, that quantity is nothing but say del rho del t over this volume integral dV. So, I can from this equation I can write that the volume integral bracket divergence of J plus del rho del t and dV is equal to 0. This is a general, for any volume it is true. So, that is why I can have the desired relationship, a very important relationship rather, with the charge density and the current density J, and this equation is called the continuity equation. But why this continuity equation is required here? So, let us now consider the steady current. So, for steady current what happened? it is 0. So, for steady current it is 0. So, that means under steady current I have a condition from the continuity equation that this has to be 0, as we know this is equal to minus of del rho del t. So, this quantity has to be 0. So, let us now try to understand this. When there is the charge is in stationary. So, for stationary charge, charges, what we get is the constant electric field. The stationary charges leads to the constant electric field. There is no change with respect to time, that is why it is called constant electric field, and that basically the our electrostatic study. On the other hand, when we have steady current, that leads to constant magnetic field. That is magnetic field that is not changing with respect to time, and that topic is under magnetostatic. This is the topic of magnetostatic, where we deal with the situation where the current is steady, and electrostatic we have already discussed the entire part, where the charge particle is always in a stationary position, it is not moving. So, now after having this idea, let us now try to understand the Biot-Savart law. So, Biot-Savart law is nothing but the magnetic field of steady current. So, the magnetic field of the steady current, if I want to calculate, so that is, there is a law, and this law is associated. So, this law is basically the Biot-Savart law. You all know this law because this is the topic which is there for a long time in the syllabus in class 12 or level. So, let us now consider a coordinate system as usual, and then I draw a wire here. Suppose this is a piece of wire, and from here to here this length is say dl prime, and the current is flowing, a steady current is flowing. So, the steady current is flowing say I, and if a current is flowing, so the law suggests that we will going to get a corresponding magnetic field, and we know that when the current is flowing through a wire, around the wire some magnetic field is produced. So, the amount of magnetic field that is produced will follow certain law. So, that is eventually the Biot-Savart law. So, suppose this is the point P where I want to find out the magnetic field, and from here the distance is say r, and the coordinate of this is say vector r. So, from here to here this is vector r. So, the location of this point is vector r. Okay. So, now if this is the case, so I just draw the geometry. So, what should be the point is what should be the magnetic field at point P. So, my magnetic field B at r should be proportional to the amount of current flow, proportional to the amount of this length, and inversely proportional to of r square. So, that we know. So, that I am writing in terms of this. So, mu 0 divided by 4 pi, then amount of current, and then for the entire where I should have d l prime cross, very important, then unit vector of this curly r divided by r square. So, that is the form of the magnetic field that one can expect at this point P. So, here I like to note that, because I am going to use these things, that divergence of the magnetic field is 0 and curl of the magnetic field that we will going to show, let us just write it, it is mu 0 j, we will going to prove that later. So, this is called the Ampere's law. And we will show that in detail, but you should note that for like electrostatic we have a divergence and curl of magnetic field here. So, the divergence of the magnetic field B is 0 and curl of B is mu 0 j. So, in comparison in electrostatic, if I write here, so the divergence of E, that was the Gauss's law, was rho by epsilon naught, and curl of E was 0. That was the electrostatic thing, and that it is the magnetostatic thing. So, you should just note that here. After that, what we do interesting, because we are going to recap the Helmholtz theorem, the famous Helmholtz theorem. We have been using this theorem for in several cases. So, let me recap that. So, recap what was there, recap of Helmholtz theorem. Helmholtz theorem. And what we are having here in Helmholtz theorem? So, any vector field F can be decomposed in terms of a scalar field small f and a vector field V. Any vector field F can be written in this way, that the divergence of a scalar field f plus the curl of a vector field b. Now, the question is, if the divergence of f is known, say it is d, and the curl of f is also known, say this is c. So, these are known. Then would it be possible to construct the value of f? And the answer was yes, because if I able to construct f and v in terms of c and d, then eventually I can construct my f. And there was a recipe, and the recipe was f, which is a function of r, should be written in this way, 1 by 4 pi integration of whatever the divergence we have here. So, let us put this divergence, the value of the divergence which is essentially a scalar field, divided by mod of r minus r prime integration over the entire volume dv prime. That was the value of the fr through which you can find the first part of this total field, total unknown vector field f. And similarly, v can be evaluated exploiting the knowledge of this curl. So, it should be 1 by 4 pi integration, then the curl that should be evaluated, say at r prime, and r minus r prime integration over this v prime. So, now here if I look the value of the thing for, so here for magnetic field B, what we see that my if r seems to be 0. Why? Because as the divergence of B is 0, and if you see that it related to the divergence of that field. So, D here, so f r has to be 0, because this quantity for magnetic field is 0. For scalar, for electrostatic field, the other way, this is not, this was non-zero. So, that means for magnetic field there is no scalar potential. This is called, this is in general called the scalar potential. Because it behaves some sort of a potential and is a scalar field, and this is called the vector potential. So, there is no scalar potential for magnetic field B. But what about the vector potential? Yeah, vector potential is very much there. So, the vector potential V, which is a function of r, is simply 1 by 4 pi integration. So, now I need to exploit the value of the curl of V, because curl of B, this value I need to put here inside this integral. So, it is mu 0 j, we did not prove, but let us exploit this, let us use this. So, I have mu 0 j, but that will be evaluated at the point r prime divided by r minus r prime and then dv prime. Okay. So, that should be. So, then if V is known, then the next step is straightforward, because my B can be, I can find out my B, and my B should be simply B is at the point R, that is simply curl of V, because as f of R is already 0. So, that quantity is simply curl of mu 0 divided by 4 pi and the integration of j evaluated at some r prime and then r minus r prime dv prime. So, I can have this value, and now I can exploit more to find out whether this expression leads to our old Biot-Savart law or not. So, eventually we will find that it leads to the expression like this, because I now I am in a position to find out my B. So, let us proceed. So, my B then at r prime is simply mu 0 divided by 4 pi. Let us put this cross inside this integral. So, I should have that this is cross, and that is operating over this vector field j prime whole divided by r minus mod of r minus r prime and over the integral dv prime. Note that this is the denominator, we have the function of r, and in the numerator I function of r prime, but this operator is a function of r only. So, if I go to the traditional way by just using the vector identity, so our vector identity Tt was curl of a scalar field f and the vector field g should be simply f then curl of g minus g cross this, and curl of whatever I am doing here is operating over r prime and r minus r prime. So, I should write first this and then curl of j r prime and then minus of j r prime cross gradient of 1 divided by mod of r minus r prime. This is the way, but you can see as I mentioned that this quantity has to be 0 because this operates on r. This is a function of r. So, but it is a function of r prime. So, when we do the derivative, we will see that this is 0. Okay. So, then I have only one term left, and if I execute this term, this is also a known term, and that thing is simply minus of r minus r prime, and then it should be r minus r prime whole cube, because this is a known thing. So, we have already done this. So, we will going to put this here in this equation here. So, eventually I will going to get simply B is mu 0 divided by 4 pi, and then if I integrate it, so it should be j r prime cross r minus r prime divided by r minus r prime cube dv prime. So, this is nothing but the Biot-Savart law. In using this volume current density. So, this is the form of the Biot-Savart law. This is the form of the Biot-Savart law that we already stated earlier. Here we are writing the Biot-Savart law in terms of the current density J. If I go back to the old expression which we write, this one. So, here if I include this R inside, if I include this current A inside, then this current can be written in terms of current density, and then this volume integral will eventually appear, and we will have the expression something like this. So, today my time is up. So, I like to conclude here. So, in today's class what we do, that we write down the Biot-Savart law and try to understand the Biot-Savart law in the context of the Helmholtz theorem, and just exploiting the knowledge of the Helmholtz theorem. We exploit the knowledge of the Helmholtz theorem and derive the Biot-Savart law once again, and in the next class we will do some kind of application of the Biot-Savart law and try to understand that if I apply the Biot-Savart law in certain system, for example, a infinitely long current carrying wire. So, how much magnetic field it will going to produce at some point, say R, and we will do this problem rigorously. Later we find that such problems will be much simplified when we use the Ampere's law, but now in the next class we do some rigorous calculation to find out that if a current carrying wire is there, maybe in different shape, what should be the amount of magnetic field it will produce at some point in space. With that note, I would like to conclude here. Thank you very much for your attention and see you in the next class.